Well, thank you everyone again to join this session. I really appreciate it. I hope after this session, some of the questions is answered. So the technology we're talking about today called the Activated Dry Electrode. And of course, this is for the battery manufacturing. So LiCap's vision is we're a global leader in dry electrode technology and manufacture. The problems we're trying to resolve is today's battery, they're expensive, they're low performance, and when you make electrodes, they use environmental toxic solvent. LiCap's Activated Dry Electrode will reduce at least 15 to 25% of the cost. And we improve 3x of power density by accident. And we completely remove toxic solvent, so it's eliminated. And we're ready to scale up. So we'll talk more in detail. So this is myself and my team. And again, I'm Linda. I'm a founder and the CEO of LiCap. And I'm a PhD with more than 100 issued patents, 25 years track record of commercializing from small products in R&D scale to mass production.
Linda, I'm sorry, real quick. I'm still seeing your title slide. I'm not seeing anything advancing. Anybody else?
Yeah, same here.
You might have to just click on your number 2 and number 3 slides to have them show for us. Number 1 is highlighted now. I can see that. There you go. Now I see number 3. I see you.
Now we see the leadership team.
Yes. Thank you.
Okay, so I'm not going to do the presentation mode. Just keep this mode.
Okay.
So I was the original inventor for dry electrode when I was working for Maxwell Technologies. And Maxwell eventually sold to Tesla in 2019 because of that technology and because of that technology only. And I'm also the new inventor for the new generation of dry electrode called Activated Dry Electrode. I will explain to you what's the difference between those technologies. And this new technology actually resolved the issues with the original dry electrode technology. If you wanted to use technology for the battery electrodes, I will explain to you why. And along my team, you have Martin and Chris. We have different expertise. Some of us on the equipment side, some of us on the business side. So this is a little bit of the history of LiCap. LiCap was formed in 2016, and along the line we developed different technologies. But all the technologies, it could be used for ultracapacitor, it could be lithium-ion capacitor, batteries, solid-state batteries, but the core technology is always the electrode, the technology we call the Activated Dry Electrode. So whatever the powder form that you provide, we can make electrodes within this technology. So most recently, we also start the sodium-ion battery Activated Dry Electrode development. So most of you probably very familiar with the wet electrode. The wet electrode existed for more than 30, 40 years, and people fine-tune, been many, many years, and this is a perfect technology. However, one thing is they made it run at the beginning, and it is still wrong, which is very high cost. The reason is that you have 5 major process steps. With the first step for the slurry mixing, you put too much solvent. The solvent amount is 30 to 40%, which is unnecessary. And on top of that, the solvent is toxic. And the slurry mix time is hours and to 10 hours, even to 20 hours to make this very, very uniform. And then you do the dye coating on the aluminum foil or copper foil. Because of the floating, you have the binder migration problems, you have a lot of issues. And then you have to dry them out, dry the solvent out. And this dryer is pretty much how the faster you want to run the machine, the longer will be your dryer. The dryer is so big, like we're talking about 100 meters, right? Maybe 50 meters to 100 meters, depends on how fast you want it to run. And then because the solvent is toxic, or even the water, even if it's water, you wanted to reclaim this, the steam, everything, you have to put in a huge recovery system. So it's another bigger area and space, another electricity usage, and else. And finally, you have to do a calendaring. So they are pretty lengthy process, and a lot of energy consumption, everything. So when you move to the dry electrode, okay, activate dry electrode, we slash down to 3 steps. So specifically, we simplified step number 1. We do not put 40% solvent anymore. We put a very small amount of solvent. I will explain to you why we put a small amount of solvent later. Just bear with me right now. So you do a quick mixing. We're talking about 5-10 minutes mixing. That's it. Okay, instead of hours of mixing. And then from the powder status. So on one side, when you look at the pot, it's a powder. Absolutely, it's a powder. And then you press it, become a freestanding film. It's electrode freestanding film. Depends on the density you want. Depends on the thickness you need. You press more times, and then you get into everything into the specification. Then you put on a current collector by elimination. So machine became very small. Okay, it's only you save space at least 65%. That's not including solvent recovery, because solvent recovery normally are outside of the building, so we don't count that. Even that you you reduce the space by 65%. Electricity you reduce 70%, because we don't have dryer anymore. We don't have the solvent recovery anymore. The mixing is only 5-10 minutes now, so very small amount of electricity. And the CapEx at least reduced 20%. Okay. So talking about cost saving, so we will go through exactly how much cost saving we will have by this process, right? So first, I separated them cost saving source 1, 2, 3, because some of the cost saving is only true for dry electrode in freestanding film form. Okay, so but the cost saving source 1 is true for almost all type of dry electrodes, including dry spray coating, including dry deposit, including other kind of dry technology. So source 1 is always there. Okay, so here you can see a direct comparison of a dry cathode line versus a wet cathode line. Okay, so the dry line, wet line, so assuming the line speed is 60 meters per minute. So keep in mind, the dry freestanding film technology, we can also run fast speed, like 60 meters per minute. And so the machine, the electrode width is 1 meter, so they're all the same. Okay, so the electrode per year you can make, how much you can make for kilowatts hour. And then you have the equipment and the facility investment, right? So for the dry cathode, for about 5 to 6 gigawatts hour, you need about 30 millions or 15 millions for anode, the 30 millions for cathode. And the rental space, you see, because the machine much smaller, so you don't have a bigger space, right? And then go through the electricity, and and then convert it to the money. So then from there you can calculate how much manufacture cost per meter square for cathode and anode, and then you convert it to kilowatts hour, and then you have the total manufacture cost per kilowatts hour, like $2.37 per kilowatts hour, right? So you do exactly the same calculation for wet process. Okay, so you end up with about $5.32, right? So here you also can see dry electrode. I put on 7 milliamp hour per centimeter square, and the wet electrode you put in 4.4 milliamp hour per centimeter square. So for one, I'm going to show you some data later. Those two electrodes, even though one is high loading, one is the low loading, they will be performing the same. So we're talking about same category of electrodes, batteries. Okay, so if you calculate it that way, you can see capex saving is about 34 millions for 5 gigawatts hour, and if you have a larger plant, capex saving is huge. It's $1.4 billion, right? So that's upfront money you can save. But for OPEX, right? So 1 kilowatts hour, you can save about $2.91. And of course, the larger the plant, the more the saving. This is, if it's 200 gigawatts hour, you save about 580 millions. That's per year. That's each year you can save. Now, when you look at $2.91 for kilowatts hour, you feel like, well, this is a small number, right? And compared to, we're talking about per kilowatts hour, total cost is like, okay, $80, $90, $2.91. It's very small, right? But everybody talking about dry electrode can save a lot, right? But you can see from this saving, from space, electricity, as well as the the equipment, the investment for the depletion, and you only save $2.91. Now, the next slide is going to show you very interesting phenomena. This is only true for freestanding film. Remember, in our technology, you do not put your electrode on the current collector until the very last moment. So anything before you put on the metal, we're talking about the powder, we're talking about freestanding film, we're talking about almost solvent-free system. It's a powder, right? So everything, if you have an edge, you need to trim off. If your electrode has some kind of defects, for example, surface defects, for example, you have some cracks, you can do 100% direct recycling just right there. In our process, you can vacuum up and go back to the powder room and chop them up to the powder status. You can reuse it just like a new material. So you only have yield loss after the lamination. Now, from there, you have at least 7% of material savings. And there, for cathode and anode savings, you have each kilowatt hour. You now can save $12. So this is, if you expand to 200 gigawatts of plant, you can save $2.4 billion per year. So this is significant savings we're talking about, right? And the cost saving number 3, and this is by accident. We didn't even. This was not the original, purpose to improve the performance and those. But this is like when we send the samples, 1C samples to customers just test them all the way to 3C and all the way to 4C, and they come back and say, hey, your electrode will work for 4C. So we test again. So from here on this chart, you can see that LiCap's 3.5 milliamp hour loading versus wet electrode 2.2 milliamp loading. So now we're talking about single layer active loading. You can see at the 3C discharge and compared to the wet electrode and the dry electrode, the thick electrode is actually dry electrode and actually more stable, right? So this is, which means we can use 3.5 milliamp hour to replace 2.2 directly. And another customer also tested our 4 milliamp hour to 5 milliamp hour compared to customers' wet electrode, which is 3.6 milliamp hour. You can see our 5 milliamp hour, the red line is not so clear to you maybe. So the red line and the green line matches exactly well, which means our 5 milliamp hour can replace their 3.6 milliamp hour. So which means, previously you need 20 stacks to get a certain energy for your battery. Now you only need 12 stacks, right? From there you can save separator now. So basically, if you use thick electrode to replace the thin electrode to make the same battery, you save a lot of materials, like separators, maybe the packaging of your battery, maybe your stacking machine you can reduce, and maybe your formation machine you can reduce, on and on. But here we only count to the raw materials and not including the battery side. So here you can see if I add everything, all those three sources together, you can see for the 5 gigawatts hour and 2,200 gigawatts hour, you have a big saving of the capex, which is a front money, front investment money, and for the OPEX, you can save about $15 per kilowatts hour. So that number is huge, right? And so from here, you see about, if you do the calculation, 15 divided by 74, it's about 16, 17. So this ratio, the saving ratio will not change if you change the chemistry. Say here, I wanted to now look into the LFP. Now I wanted to implement this technology in Korea, or I want to implement this technology in Europe. The percentage saving will stay the same, even though the absolute amount may be changed, right? So this is significant cost saving we're talking about. And our next slide, we're showing the original technology, the dry electrode, now it's owned by Tesla, versus the new technology now developed by LiCap. So the key difference is in the older technology, which was developed for ultracapacitor, and we do not do the binder activation. So everything's dry. So imagine you put the sugar on your hand. You try it; they are not sticky. But if you stretch them to the fiber, which means look like a cotton candy, it become very sticky. So this is exact the mechanism of the freestanding dry electrode mechanism, right? The bonding mechanism. So the older technology, we do not do the activation. So you can stretch the binder to fiber, but the fiber eventually gonna break if you stretch them too long, right? So in the new technology, what we do is we activate the binder first. So before they break apart, you can stretch them much longer. And you make the binder much more effective, such that you can reduce the binder by half. So if originally you need 8% binder, now you only need 4%. If originally you need 4%, now you only need 2%, right? So now you have less binder, also your fiber much thinner. You can make a lot thinner electrode. The thin electrode is very important for EV applications. Everybody knows that because it provides high power. So this is the basic reason why when you open Tesla's 4680, the cathode is still wet electrode, because it's so difficult to make a thin electrode which is strong enough, which you can run 60 meters per minute. So that's why it slows down the application of the older technology to the battery cathode. But it's perfect for anode. Why? Because the technology was invented for anode, for carbon-based electrode. So they're perfect match. Now, a lot of people were saying that when you use dry method, the older dry method, right? When you make a freestanding film, especially if you make an NMC electrode, the freestanding film looks okay, right? But if you do side-by-side comparison, you will see this is how we did it. Our engineers, from time to time, we will check on, if we don't put the solvent at all, no activation at all, what it look like. From very consistently, you will see it's harder to press down. You have more defects in the electrode freestanding film, right? So and less flexible. So flexibility, the strength are very important for the mass production when you do the scaling up. Now, if you open up, compare the freestanding film made by with activation and without the activation. Now, this is almost the best scenario when you look at the film without the activation. If you look by naked eye, they look almost the same, and you don't see much problem. But if you look on the microscope, you will see the defects. Those surface defects are the reason you cannot run them fast, because those are the weak point, high stress, stress concentration area. So when you run the film with the speed, they start to break. And if you have a film break, this is a nightmare in the mass production. In the R&D, doesn't matter. But in mass production, those are the areas you cannot run fast and you cannot reduce your cost. So very interesting, this technology. This is very unique technology, right? I can make a very thin electrode. Remember, I overcome the thickness issue by stretching the fiber much longer. So I can make a very thin electrode. I can also make a very thick electrode. This provides very wide applications. I can make the batteries for EV. I can make the batteries for grid, for ESS. So very broad application. And also it is chemistry agnostic, right? As I said, I can make ultracapacitor electrode. I can make battery electrode. I can make solid state battery electrode. I can make sodium ion battery electrodes, right? So this is just an example. Like when we make the cathode in our dry room, our active material is 80%. This is a particular case is the NMC 622. This is sulfur-based battery electrodes. So you will see it's very stable. You see that the cycle life at 100 cycles, your decay is very, very small, very stable, right? Now, now we're talking about scale up. So this is a LiCap design of our activated dry cathode line. You can see we have 1 gigawatt-hour and 5 gigawatt-hour. So the total length of this machine. So this is two film on the left side and the right side. You make two freestanding film together. In the middle, it's a lamination. It's a laminator. So you see the machine total is about 15 meters instead of 100 meters for the wet electrode, right? And then you can see the space is very small. You can see the power usage is very small. It's very precise of the cathode line. So LiCap is working with our partner to making the equipment for our customers. So I wanted to tell you where we are. So last year we formed a partnership with DIR and also another equipment supply. So 3 companies we're working together. We call it the TKSC, Turnkey Solution Consortium. And this Turnkey Solution Consortium, right now we are built up 1 gig POC line. And this line will be ready in a couple of weeks, in a couple of months for testing. And immediately after that, after we pass in the test, we're going to release the first production for our first customer for the 1 gigawatt-hour line. And then at the same time, start early next year, we're also going to start and build 5 gigawatt-hour POC line, and which will be ready for testing in 2026, and that which will be installed for our first customer in 2027. So I think that this is the end of my presentation. If you have questions, this is a good time to let's discuss.
Eric, you're first. You're muted.
Eric, you're muted.
That better. There we go. So just user interface issues. I apologize. Something I don't understand is fundamentally what's different in the process or in the manufacturing from what you do from the Maxwell process. I understand that you got your, you came from Maxwell, and so you understand both. Basically, most of the presentation could be made for the Maxwell process in terms of the benefits, for example. So I'm having a hard time figuring out what the differentiation is. You only had one illustration that showed graphically that there was some slight difference in the defibrillation point. Can you explain that a little bit more completely, please?
Yeah. So there are two key differences between the actively dry versus dry. So actively dry means we put some solvent to activate the binder, right? So imagine so our freestanding film electrode binder is, as you know, is PTFE based, right? So PTFE can be activated. For example, if you use heat, you increase the temperature for PTFE. PTFE becomes soft, right?
Mm-hmm.
But if you don't do any activation, for example, the heat or the chemical activation, then you start to do the stretching of PTFE into the fibers that they break apart very quick.
Mm-hmm.
So the actively dry versus testless dry, Maxwell's dry, the key difference is we introduce activation for the binder before we start putting the mechanical stretching for the binder. So that is in the process wise, and also in the formulation wise, there's a fundamental difference. Now, because of this activation step, we made the freestanding film much better quality, and the device you made, for example, the ultracapacitors or batteries, the device you made with much better quality. Okay, and for example, if you use the older technology, you try to make cathode, you cannot scale up, right? Because of all the problems associated with it. But if you use activated dry method, now you are able to scale up.
So essentially your difference is in the binder, and you're doing some activation of the binder first. Okay, yeah. So if I understand, the activation of the binder process would be prior to coating, shall we say. Is all the process downstream of the activation of the binder exactly the same equipment?
Activation the binder.
You're saying the binder activation is your key differentiation.
Yes.
Is all the rest of the equipment, when I'm talking about the supplier of the equipment, you have Dürr as one of your consortium participants. Is all the equipment the same as for the Maxwell process, apart from the binder activation?
So you're talking about the electrofilm and the lamination, right?
I'm talking about dry. I'm comparing two dry processes, Maxwell and yours.
Yes. So if you look at the dry process, also the Tesla dry process also contains 3 steps. They have the binder mixing, they have the electrofilm and the lamination. So you see that the first step is process different, and also the the mixing equipment are different. Okay, our mixing and their mixing is totally different, and the electrode film and the lamination. I'm not so sure about the lamination, but the electrode film, this machine making the freestanding film are absolutely different.
Okay.
Yeah.
If you're basic.
Looks like he dropped for a second, Eric. I'm sure he'll jump back on. One of the questions I had is, from the slurry mixing, when you are doing a dry cathode process, why is the mixing time so much more greatly reduced? On number one question, and number two is, are you making electrodes today?
I need to travel.
So in the slurry mixing, I guess you have to make the slurry uniform. You have to make it very slowly, like you have to use like hours to mixing them. So you have to break the particles apart inside the solvent, right? And then you need to mix them very slowly and make them uniform. In the dry powder, so as you can imagine, they don't move by itself. So that the moment that you input the energy to mix in them, so every energy you input, and then they start mixing them automatically, right? So you do not need so much time to make them uniform, and so much time to break the particles apart, so agglomerates apart. So that's why, of course, that's why I'm saying our mixer and the Tesla mixer are different, are totally different. And the one thing that you have to control your mixer is so important, so that you do not overheat your mixture powder, so which is very, very important.